If two rotating supercells merging into a single, untrackable storm, and what that does to the tornadoes nobody can see coming, has you as locked in as it has me, hit like and subscribe to Signal Watch right now so you don't miss a single update as this develops in real time. Drop a comment below and tell us where you're watching from, what time it is there, and this question. Have you ever been caught off guard by a tornado warning with less than 5 minutes of notice? Because what you're about to see explains exactly how that happens and why it's becoming more common. And if you want to help this community keep growing, share this video on X, Facebook, Reddit, or even just your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Now, a flanking line that doesn't die when two storms collide. It feeds directly into the dominant updraft and makes it stronger. Gorilla hail the size of softballs, dropping across suburban neighborhoods with zero visual warning. A violent disruption to low-level wind shear that produces tornadoes in seconds rather than minutes. And the reason the most dangerous tornado in a supercell merger is the one wrapped in so much rain that it doesn't appear on anybody's phone alert until it's already on the ground. Now, settle in and let's get into it.
There's a specific moment in radar analysis that stops experienced meteorologists mid-sentence. Not a new cell forming, not a hook echo developing in the expected position. It is the moment when two discrete supercell reflectivity signatures, each rotating, each internally organized, each displaying the full architecture of a mature, severe thunderstorm, begin to close the distance between them on the base reflectivity scan, and the signatures are moving toward each other. That moment is the beginning of a supercell merger, and what follows it is one of the least predictable, most rapidly evolving, and most dangerous scenarios in operational severe weather meteorology. To understand why, you need to understand what a supercell actually is at its most fundamental level. A supercell is not simply a large thunderstorm. It is a thunderstorm in which the updraft, the column of rapidly rising warm, moist air that feeds the storm's energy, has developed rotation. The rotation is called a mesocyclone, and it forms through the interaction between the storm's updraft and the environmental wind shear. The change in wind speed and direction with altitude that characterizes the strongly sheared environments in which supercells develop. The National Severe Storms Laboratory, which has been the primary research institution for severe convective weather in the United States since its founding in 1964 in Norman, Oklahoma, defines a supercell operationally as a thunderstorm with a deep, persistently rotating updraft. The mesocyclone is detectable by Doppler radar through the velocity couplet it produces, adjacent areas of inbound and outbound radar-detected wind velocity that indicate rotation at mesocyclonic scale, typically 10 to several tens of kilometers across. A single, mature supercell is already a system the Storm Prediction Center in Norman monitors with dedicated attention. It already has the capacity to produce large hail, damaging straight-line winds and tornadoes. Its internal organization, the forward flank downdraft, the rear flank downdraft, the flanking line of developing cumulus along its southwestern or western edge, the wall cloud, where the rotating updraft base descends closest to the surface, represents a coherent, self-reinforcing dynamic system. When two of these systems approach each other, the interaction begins before they physically merge. It begins when their low-level outflow boundaries, the density current of cooler, denser air that spreads along the surface from each storm's downdraft precipitation intersect. On the afternoon of May 3, 1999, the Norman, Oklahoma supercell that produced the Bridge Creek Moore F5 tornado was one of multiple discrete supercell thunderstorms operating across central Oklahoma. Storm interactions on that day, not the tornado itself, but the broader context of multiple organized supercells in a high shear, high instability environment, produced a laboratory of storm-scale dynamics that the researchers at NSSL have been examining ever since. The specific mergers and interactions among those storms affected their individual tornado production in ways that the operational forecast models of the time did not anticipate. 26 years later, the physics of that interaction is better understood. The ability to forecast it in real time remains one of the central challenges of severe convective meteorology. The standard description of a supercell merger in meteorology textbooks focuses on the structural outcome. Two storm systems combine, producing a larger and potentially more intense single storm. The description is accurate as far as it goes. It misses the operational significance entirely. The danger of a supercell merger is not primarily in the outcome, the larger storm that results. It is in the process. The minutes and hours during which two organized rotating convective systems are interacting, disrupting each other's internal structure, competing for the same moisture inflow, and alternately reinforcing and destabilizing each other's mesocyclones. That process is where the most dangerous meteorology happens. When a trailing supercell, a storm following behind and to the south of a lead supercell in a typical Great Plains severe weather environment, begins to close on the lead storm. The first interaction is between the respective inflow sectors. Both storms are drawing warm, moist surface air from the south and southwest. The inflow, the low-level jet and the moisture-laden boundary layer air that feeds convective storms in the central United States during active severe weather episodes, is a finite resource. Two mature supercells competing for the same inflow sector is a zero-sum dynamic. What one storm draws, the other does not receive. In many supercell interaction cases, this competition weakens the trailing storm, as the lead storm wins the inflow competition. The trailing storm's updraft weakens. Its mesocyclone loses rotation. The storm undergoes what meteorologists call storm-scale occlusion. The rear flank downdraft wraps around and cuts off the inflow, and the storm begins to dissipate. This is the outcome that forecasters watching a potential merger scenario are hoping for. But there is a second scenario, a scenario that depends on the relative geometry and motion of the two storms, the orientation of their outflow boundaries relative to the available shear, and the specific configuration of the low-level wind field between them. In this second scenario, the flanking line of the trailing storm, the band of developing convective towers along the storm's southwestern edge, where fresh inflow is being lifted and new convective cells are continuously forming, does not die as the trailing storm weakens. Instead, it connects. The flanking line of the trailing storm feeds directly into the inflow sector of the lead storm. The developing cumulus towers along that flanking line, towers that were growing in service of a trailing storm that is now losing its own organization, become new ingested energy for the lead supercell. The lead storm's updraft, which was already drawing from the available inflow sector, now receives an additional energy injection from the absorbed flanking line of its dying competitor. What follows is not simple addition. What follows is explosive. The absorbed flanking line delivers both additional moisture and additional vorticity, the rotational tendency in the low-level flow, to the lead storm's updraft base. The lead storm's mesocyclone, already rotating, receives a fresh infusion of low-level rotation. The rear flank downdraft intensifies. The wall cloud descends, and the mesocyclone, now fed by two converging streams of rotating inflow, rapidly increases its rotational velocity. Doug Burgess at the National Severe Storms Laboratory, whose research on low-level mesocyclone structure and tornado genesis has included extensive analysis of storm merger cases, documented this intensification mechanism in detail. His work established that the convergence line produced at the boundary between the two storms' outflow boundaries is a critical zone for rapid vorticity enhancement, and that the most rapid tornado development in merger cases frequently occurs within minutes of this convergence line interaction. Minutes, not hours. Minutes, before this investigation can address the rain-wrapped tornado phenomenon. The piece that makes supercell mergers so specifically lethal in populated areas, it needs to address what happens to the hail core. Hail forms in the updraft of a thunderstorm. Ice embryos, typically formed on tiny particles of dust or other nuclei, are lofted into the supercooled water droplet environment of the upper level updraft, where they accumulate successive layers of ice. The size of hail at the surface is a function of the updraft velocity and the time the hailstone spends in the growth zone. Stronger updrafts support larger hailstones. The relationship between updraft velocity and hail size is not linear. It scales roughly with the square of the updraft speed. A mature supercell in a high shear, high instability environment typically produces updraft velocities estimated at 150 to 200 kilometers per hour, based on dual polarization, Doppler radar retrievals, and aircraft penetration data. At those updraft velocities, hailstones of 2 to 4 centimeters diameter, golf ball size, are routinely produced and sustained in the updraft before falling to the surface. When a supercell merger delivers an additional energy injection into the lead storm's updraft, the updraft velocity increases. It does not increase modestly. The additional latent heat release from the absorbed flanking line, combined with the enhanced convergence at the low levels from the two storms' outflow boundary interaction, produces a rapid updraft intensification that researchers have characterized in post-event analysis as updraft velocity, increases of 30 to 50% above the pre-merger state in some documented cases. 30 to 50% updraft velocity increase, applied to the hail size relationship. Squared, a storm already producing golf ball hail at baseline updraft velocity, experiencing a 30 to 50% updraft increase, can transition to baseball size or larger hail within the time it takes a single updraft pulse to cycle through the storm's glaciated upper level cloud. That transition, from golf ball to baseball or beyond, happens in minutes, not in the extended hail event that would allow radar operators and warning meteorologists to detect the change and update their public advisories. The term gorilla hail, hailstones in the 100 millimeter range or larger, sometimes called softball hail in operational meteorology, is not a formal meteorological classification. It is operational shorthand used by storm chasers, NSSL researchers, and NWS warning meteorologists to describe the largest category of damaging hail events. The largest hailstone on record in the United States was recovered in Vivian, South Dakota on July 23, 2010, measuring 20.3 centimeters in circumference and weighing approximately 875 grams. That event occurred in a storm with characteristics: extraordinarily strong updraft velocity, estimated above 220 kilometers per hour, consistent with what a supercell merger can produce when the inflow and shear alignment is optimal. The gorilla hail problem in a supercell merger scenario is not just a property damage issue, it is a visual obstruction issue. The large hailstones falling through the precipitation core of the intensifying lead storm, combined with the dramatically increased precipitation rate from the absorbed moisture, produce a precipitation shaft of such density that the tornado, which is forming or has formed in the rear flank, down, draft region adjacent to the precipitation core, is completely embedded in a visual curtain of rain and hail. This is the rain-wrapped tornado problem, and it is not a theoretical risk in a supercell merger. It is the expected outcome. The visual identification of a tornado by the public depends on contrast. Dark rotation against a lighter background sky, a condensation funnel descending from the base of the wall cloud, a debris cloud rising from the surface below the circulation. Any of these visual cues can alert a person in the path of a tornado to their danger in advance of a phone alert or siren activation. A rain-wrapped tornado removes every one of these cues, not selectively, completely. The condensation funnel, the visible portion of the tornado formed by the condensation of water vapor in the low-pressure core of the vortex, is obscured by the precipitation curtain. The debris cloud, which in a violent tornado striking open terrain can be visible for tens of kilometers, is buried inside the precipitation shaft. The contrast between the rotating circulation and the background sky is eliminated by the wall of rain and hail through which an observer would need to see in order to detect the tornado's presence. The meteorological conditions that produce a rain-wrapped tornado in a supercell merger are not accidental. They are the direct consequence of the dynamics we've been building through this investigation. The dramatically increased precipitation rate in the lead storm's core, fueled by the absorbed moisture from the trailing storm's flanking line, creates the precipitation curtain. The rear flank downdraft, the descending dry air from the storm's southwestern flank that wraps around the mesocyclone and focuses low-level convergence and vorticity, is now embedded within this precipitation curtain rather than emerging from its edge. The tornado that forms at or near the tip of the rear flank downdraft boundary is inside the rain. The National Weather Service's Warning Decision Training Division has developed training materials specifically addressing rain-wrapped tornadoes because the meteorological conditions that produce them, high precipitation of supercells, which have higher environmental moisture content than classic supercell structures, and supercells in merger scenarios are specifically associated with reduced public warning times and elevated fatality rates relative to visually observable tornadoes. The research supporting this association was developed in part by Harold Brooks at the National Severe Storms Laboratory. His analysis of tornado fatality data, published across multiple studies, established that tornadoes occurring at night, in winter, and in high precipitation environments have significantly higher fatality rates per tornado than tornadoes occurring under conditions allowing visual identification. The mechanism is not the tornado's physical characteristics. It is the reduction in the warning time that allows people to reach shelter. During daylight, in a classic low precipitation supercell environment, an experienced storm spotter positioned appropriately can identify a developing tornado 5 to 10 minutes before it reaches a populated area. 5 to 10 minutes is survivable. People can move to interior rooms. Shelters can be reached. In a rain-wrapped scenario from a supercell merger, that visual warning time collapses to near zero for the public. The tornado exists. The Doppler radar at the nearest WSR 88D weather surveillance radar station is detecting the rotation. The warning may be issued, but from the perspective of anyone in the tornado's path who has not yet received an electronic alert, there is no visual confirmation. The first indication may be the arrival of the wind itself. The WSR 88D network, the network of weather surveillance radar units maintained by the National Weather Service, the Department of Defense, and the Federal Aviation Administration across the continental United States, is one of the most impressive operational meteorological instrument networks in the world. The 159 operational radar sites provide Doppler velocity and reflectivity coverage of the contiguous United States with a revisit time of approximately 4 to 5 minutes for a full volume scan. 4 to 5 minutes between complete scans of the atmosphere. That interval is the fundamental temporal resolution of the warning system for rapidly evolving convective events. In a supercell merger scenario, a great deal of meteorology can happen in 4 to 5 minutes. The dual polarization upgrade to the WSR 88D network, completed between 2011 and 2013, added horizontal and vertical polarization channels to the standard single polarization reflectivity and velocity data. The dual polarization data provides information about the shape and phase of precipitation of particles, distinguishing rain from hail, identifying the melting layer, and producing the correlation coefficient and differential reflectivity products that experienced warning meteorologists use to assess hail size and precipitation type in real time. These products are genuinely useful for detecting the gorilla hail core and the precipitation structure of a merging supercell system. They are not a solution to the rain-wrapped tornado warning problem. The fundamental challenge is beam geometry. The WSR 88D radar beam, transmitted at a fixed elevation angle and scanning in azimuth, samples the atmosphere at a height that increases with range from the radar. At 60 kilometers from a radar site, a typical distance for a storm affecting a suburban area, the lowest available tilt of approximately 0.5 degrees, samples the atmosphere at approximately 500 meters above ground level. At 100 kilometers from the radar, that same 0.5 degree beam is sampling at approximately 800 meters above ground. Tornado circulations are surface phenomena. The most critical low-level rotation, The tight, compact vortex near the surface where the tornado is actually producing damage is often below the lowest radar beam at moderate range. The radar detects the mesocyclone at mid and upper levels with high fidelity. It detects the near-surface tornadic circulation only when it has sufficient vertical depth to reach the beam height, which, in rapidly developing tornadoes from merger events, may not occur until the tornado is already on the ground. The dual polarization tornado debris signature, the identification of non-meteorological debris lofted by a tornado using the characteristic polarimetric signatures of tumbling debris, can confirm a tornado is on the ground. It cannot confirm this until the tornado has already struck something. The warning, in that case, arrives after the damage begins. This is not a failure of the warning decision, training division, or the meteorologist staffing NWS forecast offices. It is a geometric limitation of the instrument network, compounded by the specific meteorological character of rain-wrapped supercell merger tornadoes that makes them most dangerous precisely where the radar sees least clearly, at low levels, at moderate range, in dense precipitation. The Storm Prediction Center's convective outlooks, the Day 1, Day 2, and Day 3 severe weather probability products issued from Norman, Oklahoma, can identify the environments conducive to supercell mergers and rain-wrapped tornadoes hours to days in advance.
The transition from environmental identification to specific storm scale warning remains, in merger scenarios, the hardest operational problem in severe convective meteorology.
Here is where the investigation earns its technical authority, because a supercell merger is not a single event that appears on one radar scan and resolves on the next. It is a process, a sequence of structural changes visible in the four-dimensional radar data that experienced meteorologists can track scan by scan, and that tells a specific, identifiable story if you know what you're reading. The first sign of an impending merger on base reflectivity, the standard radar product showing the intensity of precipitation returns, is the appearance of a reflectivity bridge. As the trailing storm's flanking line extends northeastward toward the lead storm's inflow sector, the developing cumulus towers along that flanking line produce low to moderate reflectivity returns in the space between the two storms. The bridge is not initially impressive, 30 to 45 dBz returns, moderate precipitation, and what was previously clear air between two storm systems. Experienced radar analysts at NWS forecast offices watching a potential merger scenario key on that bridge, its orientation relative to the lead storm's hook echo, whether it is connecting to the inflow notch, the region of relatively clear air immediately to the south of the lead supercell's mesocyclone, where the low-level inflow is drawn into the updraft, whether the velocity data in the bridge region shows the inflow-directed motion that would confirm the flanking line is feeding rather than competing. The velocity product is equally critical. The WSR 88D's Doppler velocity data shows, at the merger's initial stages, the outflow boundary from the trailing storm as a fine line of enhanced reflectivity, a thin band of increased moisture and convergence at the surface, marking the leading edge of the trailing storm's downdraft outflow. When that fine line intersects with the lead storm's inflow sector, when the outflow boundary from one storm crosses into the convergence zone of the other, the meteorologist watching the velocity data sees an enhancement of the rotational couplet in the lead storm's base that can be dramatic and rapid. It is this velocity couplet enhancement that triggers the warning upgrade decision. The rotational velocity, computed from the maximum inbound and outbound velocities in the mesocyclone at low levels, is the primary discriminating parameter between a rotating thunderstorm and an imminent tornadic thunderstorm. When that rotational velocity at low levels increases by 20 to 30 knots within a single volume scan cycle, a change visible in the mesocyclone detection algorithm output in the WSR 88D's base data and in the algorithmically enhanced MRMS, or multi-radar multi-sensor, product, the meteorologist has between 4 and 5 minutes before the next volume scan confirms or denies what the velocity data is suggesting. And this is where the mid-investigation turn arrives, because at the same moment that the velocity couplet is enhancing, the reflectivity data is also changing in the way this investigation has been building toward. The precipitation core of the lead storm, the highest reflectivity region, typically displaced several kilometers from the mesocyclone center, is rapidly expanding as the absorbed moisture from the flanking line reaches the updraft. The reflectivity values in the precipitation core are increasing, and the region immediately adjacent to the mesocyclone, the region where, in a classic supercell, a clear inflow notch allows a visual observer to see the wall cloud and developing tornado, is filling in with 40 to 55 dBz precipitation. The hook echo is being buried. The tornado, if it is forming, is inside the precipitation. The warning meteorologist is working from velocity data and algorithm output, not from storm spotter visual confirmation. The 4 to 5 minute scan interval is the time resolution within which the most critical meteorology is occurring. And this is where the story takes a turn that most severe weather coverage never reaches. The specific mechanism by which the outflow boundary interaction in a supercell merger disrupts the environmental wind shear in a way that produces tornado genesis on a timescale of minutes rather than the longer organizational period, typical of isolated supercell tornado development. The environmental wind shear that supports supercell development and tornado genesis has two components that are operationally monitored separately. The first is bulk wind shear. The vector difference between wind at two levels, typically 0 to 6 kilometers above ground level, which represents the deep layer shear that drives supercell updraft rotation at the mesocyclone scale. The second, and more directly critical for tornado genesis, is low-level shear, specifically the 0 to 1 kilometer or 0 to 500 meter shear, sometimes called streamwise vorticity, in the low-level inflow layer, which represents the rotation immediately available to be tilted into the vertical by the updraft and concentrated into a tornado. In the ambient environment before a supercell merger, the low-level shear is set by the synoptic and mesoscale environment, the surface boundaries, the low-level jet stream, the interaction between warm and cold air masses. The NWS Storm Prediction Center's operational products, including the significant tornado parameter and the storm relative helicity calculations, use Rawlinson balloons observations and model analyses to estimate this low-level shear in the environment through which supercells are moving. These calculations are made for the ambient environment. They are not made for the storm scale environment created by the merger itself. When two supercell outflow boundaries intersect, the local wind field at the surface in the intersection zone becomes something that no Rawlinson launched 50 kilometers away and 4 hours ago can represent. The convergence of two outflow density currents, each carrying the surface level circulation signature of a different mesocyclone, creates a zone of dramatically enhanced local low-level wind shear in the minutes around the intersection. This zone is not large. It may cover only a few square kilometers. But if the mesocyclone of the lead storm is positioned over or near that zone, the enhanced low-level shear is directly ingested into the base of the updraft. The result is what researchers studying merger cases have described as rapid vorticity, amplification at storm scale, a sudden increase in the rotation at the lowest levels of the mesocyclone that can drive tornado genesis on a timescale that shortens the effective lead time of any tornado warning issued before the merger convergence occurs. Roger Edwards at the Storm Prediction Center, whose detailed analyses of significant tornado events have included multiple merger cases, documented this process in post-event reports on several notable tornado outbreaks. His analysis of the May 19, 2013 El Reno, Oklahoma event, a different type of interaction but involving outflow boundary convergence, highlighted how outflow boundaries that were not adequately represented in the pre-storm analysis altered the effective low-level shear in ways that produced more rapid tornado intensification than the operational model suggested. The El Reno tornado reached a confirmed maximum width of 4.2 kilometers, the widest tornado ever measured in the United States, in part because of the low-level convergence dynamics that the boundary interactions produced. The warning meteorologists tracking that storm were working with every tool available and still encountered a storm that evolved faster than the operational analysis framework could represent. In a supercell merger, these boundary interactions are happening simultaneously with the inflow absorption and the precipitation core expansion and the velocity couplet intensification. The meteorologist is managing 4 or 5 simultaneous rapidly evolving indicators at 4 to 5 minute resolution. The tornado, if it develops in the merger convergence zone, may be on the ground before the next radar scan confirms what the previous scan was suggesting. The physics of a supercell merger operates identically over open farmland and over dense suburban development. The meteorology does not care whether the land below is pasture or parking lot. The tornado that forms inside the rain curtain of a merging supercell will follow whatever track the storm scale dynamics direct it, and that track does not preferentially avoid cities. But the consequence of a rain-wrapped tornado is not identical across land use types, and the specific risk to suburban areas from supercell merger tornadoes is substantially elevated relative to the risk to rural areas, for reasons that compound the warning time problem we've been building throughout this investigation. The first is population density. A rain-wrapped tornado crossing open farmland may travel for kilometers without encountering a substantial structure. The same tornado crossing a suburban residential neighborhood, grid streets, houses with slab-on-grade construction, minimal interior shelter options, may encounter thousands of residents who have received insufficient warning time to reach shelter, and whose structures offer limited protection from direct tornado strike. The second is shelter accessibility, the rural Great Plains tradition of storm cellars and underground shelters, purpose-built tornado shelters that are genuinely protective against all but the most violent direct strikes is not replicated in suburban housing stock. A storm cellar that has been standard in rural Oklahoma farmsteads for a century does not exist in the typical suburban development built in the Dallas-Fort Worth Metroplex, the Oklahoma City Metro, or the suburban ring surrounding Kansas City or Wichita. The interior room on the lowest floor, the standard NWS shelter recommendation for those without purpose-built shelters, provides meaningful but limited protection from the EF3 and EF4 tornadoes that supercell mergers can produce. The third is the noise environment. The indoor shelter-in-place recommendation depends on hearing or seeing a tornado warning. In a suburban environment during a major storm, with the noise of wind, rain, hail, and potentially a tornado approaching, the outdoor sirens that many tornado warning systems rely upon as a primary public alert mechanism are frequently inaudible inside modern well-insulated houses. The transition from outdoor siren to wireless emergency alert on cellular devices has improved this. The cell broadcast system that delivers WEA messages does not depend on the recipient hearing an outdoor siren, but the WEA system's polygon-based delivery depends on the warning meteorologist having accurately defined the tornado's position and track at the time of issuance, a task that is most difficult precisely in the rain-wrapped, rapidly evolving merger scenario we've been examining. The fourth is the visual confirmation habit. In rural areas with storm awareness culture, the Great Plains region where multi-generational severe weather experience has built a population deeply familiar with tornado threat cues, the absence of visual confirmation may be understood as a reason to take shelter rather than a reason to disregard the warning. In suburban areas where severe tornado events are less frequent in lived experience, the absence of a visible funnel cloud is sometimes interpreted incorrectly as a reason not to take immediate shelter action. The rain-wrapped tornado's invisibility interacts with this behavioral pattern to reduce the effective response to warnings even when those warnings are accurately issued. A supercell merger does not typically occur as an isolated event. It occurs within the context of a broader severe weather episode. A high shear, high instability atmospheric pattern that supports not 2 supercells, but potentially dozens, distributed across a corridor of the central and southern United States that can stretch from Texas to Indiana over the course of a single convective day. The Storm Prediction Center's Operational Severe Weather Day begins the night before with a mesoscale discussion, an internal communication among SPC meteorologists that identifies the atmospheric setup, the critical uncertainties, and the potential for significant severe weather. The SPC then issues convective outlooks beginning at the Day 3 timescale, with Day 1 outlooks issued multiple times throughout the convective day as the mesoscale analysis of the actual developing weather evolves. The categorical outlook areas, general thunderstorm, slight, enhanced, moderate, and high, reflect the SPC meteorologist's assessment of the probability and coverage of various severe weather threat types. The moderate risk designation, covering areas where there is a 20 to 45% probability of tornadoes within 40 kilometers of a point, triggers specific emergency management responses in many jurisdictions. The high risk designation, above 45% tornado probability, is used sparingly, typically for days when the atmospheric setup is judged to be genuinely exceptional. The April 27, 2011 outbreak, the largest tornado outbreak in recorded history, produced 348 confirmed tornadoes in a single 24-hour period, including 4 EF5 tornadoes and 11 EF4 events. The total number of fatalities was 324 across 6 states. The SPC had issued a high-risk designation for portions of the outbreak area the day before. That outbreak involved multiple supercell mergers across the affected region. The northern Alabama storms, particularly the Hackleburg-Phil-Campbell EF5 and the Tuscaloosa-Birmingham EF4, which together accounted for a significant fraction of the day's fatalities, occurred in an environment where multiple supercell systems were in close proximity and interacting through outflow boundary convergence throughout the afternoon and evening. The SPC's storm data documentation of that event identified numerous instances where storm interactions altered the expected behavior of individual cells, accelerating tornado production, extending tornado path lengths, and producing rapid intensification of mesocyclones within timeframes that shortened effective lead times. The operational challenge on a day like April 27, 2011 is not the identification of the severe weather threat at the regional scale. The SPC had that right, days in advance. The challenge is the local scale, storm scale evolution within the broader pattern. The specific storm interactions, the specific merger events, the specific rain-wrapped tornadoes that occur within an already overwhelmed warning system processing simultaneous events across an enormous geographic area. The deployment of the WSR-88D network across the continental United States, completed in the mid-1990s, represented the most significant improvement in tornado warning capability in the history of the National Weather Service. The addition of Doppler velocity capability, the ability to detect the motion of precipitation particles and infer the wind field from those motions, transformed tornado warning from a primarily visual and spotter network dependent enterprise to one grounded in remote sensing data with quantitative rotational velocity measurements. The pre-Doppler median tornado warning lead time across the United States was approximately 3 minutes, barely enough time to reach shelter in even the most prepared household. The post-Doppler median lead time reached approximately 13 minutes by the late 1990s and has remained in that range with incremental improvements since. 13 minutes is meaningful. Research by Kevin Simmons at Austin College and Daniel Sutter at Troy University, published in the journal Weather, Climate, and Society, has established through statistical analysis of tornado fatality data spanning the pre-Doppler and post-Doppler eras that the Doppler upgrade produced a statistically significant reduction in fatalities per tornado. The quantification of the warning-led time effect on fatalities confirms that every minute of additional warning time matters, and that the reduction from 13 minutes to near zero in rain wrapped merger scenarios is not an abstract meteorological distinction. It is a life safety consequence. The dual polarization upgrade, adding the differential reflectivity and correlation coefficient products that provide phase and shape information about precipitation, added the tornado debris signature capability that can confirm a tornado is on the ground from radar data alone without storm spotter visual confirmation. The debris signature requires lofted debris to reach the radar beam height, which, as discussed, can lag the actual tornado genesis by minutes at typical warning range distances. The phased array radar technology, currently in research and development at the National Severe Storms Laboratory, offers the most promising path to closing the temporal resolution gap. A phased array radar system can complete a full volumetric scan in approximately 1 minute rather than 4 to 5, potentially quadrupling the temporal resolution of tornado warning data. The multifunction phased array radar program, which NSSL has been developing and testing at its Norman facility, demonstrated the capability in research mode. The transition to operational deployment faces the funding, logistics, and network replacement challenges inherent in upgrading a 159-site national network.
The gap between what phased array technology could provide and what the operational network currently delivers is the gap within which supercell merger rain-wrapped tornadoes are most dangerous. It is a known gap. It has been quantified. The meteorological case for closing it is not contested.
The geography of tornado risk in the United States has not changed. The geography of population exposure to tornado risk has changed substantially and continues to change in a direction that increases the consequences of exactly the warning time deficient scenario a supercell merger produces. The traditional conception of Tornado Alley, the corridor of maximum tornado frequency extending roughly from northern Texas through Oklahoma, Kansas, and Nebraska into South Dakota, reflects the historical center of the climatological severe weather distribution. But the population density of Tornado Alley, while significant in the Oklahoma City and Dallas-Fort Worth metro areas, is lower than the population density of the southeastern United States. A growing body of research has identified a shift, or more precisely an expansion, of the climatological tornado occurrence pattern toward the southeast. Research by Victor Gensini at Northern Illinois University and Harold Brooks at NSSL, published in NPJ Climate and Atmospheric Science in 2018, used environmental proxy data to examine trends in tornado activity across the continental United States from 1950 to 2015. Their analysis found a statistically significant increase in tornado activity in portions of the Mid-South, Arkansas, Mississippi, Tennessee, Alabama, and a corresponding decrease in portions of the traditional Tornado Alley, particularly the northern High Plains. The Mid-South states that are experiencing increasing tornado activity are also characterized by higher population density than the traditional Tornado Alley, older and less tornado-resistant housing stock, more forested terrain that reduces visual warning range and produces more frequent nocturnal tornado events and lower rates of purpose-built tornado shelter installation. The specific combination of rain-wrapped merger tornadoes and the southeastern population and housing stock is particularly dangerous. The visual warning cue that a storm spotter positioned appropriately can provide in a classic Oklahoma supercell scenario is substantially less available in forested terrain. The storm cellar that might be present in a rural Oklahoma farmstead is not present in a Mississippi or Alabama rural residence. The legacy mobile home park that is disproportionately represented in the lower income rural South is among the most tornado vulnerable structures in existence. The FEMA P361 Safe Room Guidance specifically addresses the inadequacy of mobile homes as tornado shelters. The fatality record from the April 27, 2011 outbreak, which killed 324 people, the majority in Alabama, and from the events of May 22, 2011 in Joplin, Missouri, which killed 161 people, reflects this population exposure pattern. These were not failures of the meteorological warning system. The warnings were issued. The lead times were reasonable for the events. The fatalities reflected the intersection of exceptional storm intensity with housing stock and population density that amplified the consequence of even well-warned events. A supercell merger producing rain-wrapped tornadoes in this environment, reduced lead time, visually invisible tornadoes, high-density population in vulnerable housing is the convergence of every unfavorable factor in the severe weather risk matrix. The risk calculus of a supercell merger changes substantially after sunset, and the atmospheric dynamics that produce the most dangerous merger events do not preferentially limit themselves to daylight hours. The low-level jet, the narrow band of fast-moving air at approximately 1 to 2 kilometers above ground level that provides a critical moisture and wind shear source for overnight convection in the central United States, typically strengthens after sunset as the nocturnal boundary layer decoupling allows the jet to accelerate without the friction imposed by the daytime mix layer. The result is that overnight, severe weather in the central and southern United States is frequently characterized by stronger low-level shear than the corresponding daytime environment. Stronger low-level shear means more tornado genesis potential. More tornado genesis potential in a nocturnal environment, where warning response times are degraded by sleeping populations, where outdoor sirens are less effective at penetrating residential structures, and where the visual cues that would be unavailable anyway in a rain-wrapped scenario are additionally lost to darkness. Creates a risk scenario that researchers studying tornado fatalities have identified as disproportionately lethal. Harold Brooks's fatality analysis, extended by Andrew Coniglio and colleagues at NSSL in subsequent work, established that nocturnal tornadoes, those occurring between 10 p.m. and 6 a.m. local time, have fatality rates per tornado approximately 4 to 5 times higher than daytime tornadoes of comparable intensity, 4 to 5 times higher, not for a rare or unusual storm type. For tornadoes that are a regular product of the nocturnal, severe weather environment that the United States experiences throughout the spring severe weather season, when the nocturnal low-level jet enhancement provides the shear environment for a supercell merger, and when that merger produces rain-wrapped tornadoes, and when those tornadoes arrive at a suburban or rural residential area between midnight and 3 a.m., the effective warning response rate drops to levels that no amount of meteorological skill can compensate for. The people in the path are asleep. The outdoor siren cannot be heard through closed windows and the noise of rain and hail. The wireless emergency alert on the phone on the nightstand may or may not wake a heavy sleeper in time. The National Weather Service's Warning Decision Support System, Integrated Information, or WDSS-2, and its successor integrated warning systems provide the meteorologist on duty at the Regional Forecast Office with the best available tool suite for tracking these events. The meteorologist staffing that office at 2 a.m. on a Wednesday in May, managing a complex supercell cluster across multiple counties in simultaneous warning status, is working at the limit of what a single person can track with 4 to 5 minute radar resolution. This is not a critique of NWS meteorologists. They are, by every assessment, performing an extraordinarily difficult task with genuine skill. It is an honest statement of the system's physical constraints in the scenario that produces the greatest harm. The question of whether a warming climate is changing the frequency or intensity of supercell thunderstorms and tornadoes is one of the most actively researched and genuinely contested questions in atmospheric science. The honest answer, the one that the best current research supports, is that the picture is complex, and the signal is not yet cleanly emerging from the noise of natural variability. What the research does show clearly is that the thermodynamic environment within which severe convective storms develop is changing in ways that are physically consistent with more intense convective events when they do occur. Convective available potential energy, CAPE, the measure of atmospheric instability that determines how much energy a developing thunderstorm can extract from the unstable atmosphere, is driven by temperature and moisture in the lower atmosphere. A warmer atmosphere holds more moisture. The Clausius-Clapeyron relationship we encountered in the Atlantic storm investigation is equally applicable here. More moisture in the boundary layer means higher dew point temperatures. Higher dew point temperatures mean higher CAPE values. Synoptic scale analyses of the CAPE environment during significant tornado outbreaks show that several of the highest CAPE events in the historical record have occurred in the past 2 decades. The 2011 outbreak environment, the 2013 Oklahoma City outbreak environment, and multiple events in the 2019 and 2021 seasons recorded CAPE values in excess of 4,000 to 5,000 joules per kilogram across large areas. Values that represent thermodynamic instability at the high end of what the Radiosonde Observation Network has measured in the continental United States. High CAPE values do not directly cause supercell mergers. They do not change the geometric dynamics that determine whether a trailing storm's flanking line feeds into or competes with a lead storm's inflow. But they do provide the raw energy reservoir from which a merging supercell system can draw. A merger occurring in a 5,000 joule per kilogram CAPE environment has more available energy for updraft intensification, hail growth, and mesocyclone amplification than the same merger geometry occurring in a 3,000 joule per kilogram environment. The potential intensity ceiling for the merged storm, the maximum updraft velocity, the maximum hail size, the maximum mesocyclone rotational velocity, scales with the available instability. A warming atmosphere that systematically elevates boundary layer moisture and CAPE values is a warming atmosphere that raises the upper end of the severe weather consequence distribution. Whether individual tornado events are becoming more frequent is a question the data has not yet resolved cleanly, given the non-meteorological factors. Population density increases, improved damage surveys, expanded storm chasing documentation that affect the historical tornado record. Whether the most intense events, when they occur, are drawing on a more energetically loaded atmosphere is a question the thermodynamic data answers more directly. The atmosphere is more loaded. The storms that form in it have access to more fuel. The mergers that occur within that environment have a higher ceiling. The Storm Prediction Center in Norman, Oklahoma, occupies a building that has seen more significant weather forecasts issued than any other address in the history of operational meteorology. The meteorologists there are, collectively, the best severe convective forecasters in the world. Their tools, the Operational Rapid Refresh and High-Resolution Rapid Refresh models, the HREF Ensemble, the Experimental Convection Allowing Model Guidance from NOAA's Global Systems Laboratory, the Dual Polarization Radar Mosaic, the MRMS system, represent the current state of the art in severe weather prediction, and they cannot reliably predict a specific supercell merger. This is not a reflection of institutional inadequacy. It is a reflection of the physical predictability limits of storm-scale convection. The theoretical predictability limit of convective systems, the timescale beyond which the chaotic dynamics of atmospheric convection make useful deterministic prediction impossible, is estimated by research groups working on convective predictability at approximately 12 to 48 hours for regional convective mode, and substantially less for individual storm evolution within a convective system. What the SPC can forecast with meaningful skill is the environment that supports supercell development, the probability of supercells in the region, the probability of tornadoes given supercell development, and the broad geographic distribution of threat. The Day 1 Outlook issued each morning provides genuine value. It tells emergency managers, television meteorologists, school administrators, and state emergency management directors where the risk is concentrated. What the Day 1 Outlook cannot provide is the identification of which two storms out of the 12 or 20 or 30 supercells that will develop in the Outlook area will find themselves in a merger geometry at a specific time and location. That specificity requires storm scale information that only becomes available as the storms themselves are observed by the radar network. The transition from the SPC's environmental outlook to the NWS Forecast Office's storm scale warning is the gap where the specific risk of supercell merger tornadoes lies. The SPC can set the stage. The NWS meteorologist watching the radar has the task of identifying the merger as it is occurring and issuing the tornado warning, ideally with enough lead time that the people in the path can respond.
The average tornado warning lead time in the NWS system is approximately 13 minutes for all tornadoes. For rain-wrapped tornadoes from supercell mergers, where the debris signature may be the first confirmation and the debris signature requires an already striking tornado, that lead time can drop to 4 to 5 minutes or less. In some documented cases, it drops to 0. The tornado is confirmed on the ground before a warning is issued. The gap between 13 minutes and 0 is the operational space this investigation has been mapping.
At the point where the investigation's evidence chain is complete, the honest assessment requires naming 3 genuinely different outcomes for a supercell merger event impacting a populated area. outcomes that differ not in degree but in kind. The first interpretation is the outcome that operational meteorology is calibrated to produce. In this reading, the merger is identified early. The reflectivity bridge between the two storms is detected on the initial scans when it is still a weak to moderate connection. The velocity data shows the mesocyclone intensification before the convergence line has reached the inflow sector of the lead storm, and the warning is issued while the lead time is still in the 8 to 13 minute range. The wireless emergency alerts reach the phones of the people in the storm's path. The outdoor sirens activate. The majority of residents in the warning polygon take shelter action. The tornado, even if it is rain-wrapped and visually invisible, strikes a population that has had sufficient time to reach interior rooms or purpose-built shelters. In this outcome, fatalities occur. Some people are in vehicles, some fail to receive the alert, some are in structures that do not provide adequate shelter. But the event is survival at the community level. The warning system performed as designed. The outcome reflects the residual risk that the system cannot eliminate, not a failure of the operational chain. This outcome requires early radar detection, experienced meteorological analysis, rapid warning issuance, effective public communication, and appropriate shelter response. Every link in the chain must function, most of the time, in well-monitored environments with established severe weather culture and electronic warning infrastructure. It does. The second interpretation is the intermediate outcome, where one or more links in the chain fail to perform optimally. The merger occurs in a radar data gap between two WSR-88D sites, where the beam heights at the merger location are sufficiently elevated that the near-surface circulation is below detection threshold until the tornado is already on the ground, or the merger occurs at a range where the 4 to 5 minute scan interval catches the tornado genesis event between two consecutive scans. The pre-merger scan shows an intensifying mesocyclone, but no confirmed tornado. The post-merger scan shows the debris signature of an already striking tornado. The lead time is 3 to 5 minutes. In this outcome, warning issuance occurs. People who are awake and have their phones on receive the alert and respond. People who are asleep or whose phones are silenced or who are in the outer portions of the warning polygon and underestimate their proximity to the storm's actual track do not respond effectively. Fatalities occur in single-digit to low double-digit numbers. Significant property damage occurs across the path. The post-event analysis identifies the beam geometry gap or the scan timing gap as the proximate cause of reduced lead time, and the after-action report recommends additional phased array radar sites at the identified gap locations. This outcome recurs. It has recurred multiple times in the record. The identifying features, a gap in effective low-level radar coverage at the critical range for the event, are known and mapped and have been the subject of funding requests that have not been fully acted upon. The third interpretation is the outcome that the evidence does not rule out and that the most consequential merger cases in the historical record have approached. In this reading, the merger occurs in a nocturnal environment, in a region of expanded tornado activity outside traditional tornado alley, in a community without embedded severe weather culture and with high rates of vulnerable housing stock, in a radar coverage gap, on a night when the warning meteorologist is already managing simultaneous severe weather events across multiple counties at the limits of single operator workload. The tornado is on the ground for 5 minutes before the debris signature confirms it. The warning is issued. The wireless emergency alert has a 3 to 4 minute delivery lag in some cellular network architectures under high traffic load from simultaneous emergency communications. The people in the direct path have fewer than 60 seconds of confirmed warning. The tornado is EF4 intensity, produced by a merger mesocyclone that amplified from the convergence of two outflow boundaries in a 5,000 joule per kilogram CAPE environment. This outcome is not hypothetical. It is the generalized description of multiple events in the historical record. The April 27, 2011 Hackleburg event, the May 22, 2011 Joplin event, the events of December 10, 2021 that produced a tornado outbreak across the Mid-South and Central United States, including the Mayfield, Kentucky, EF4 that killed 77 people in what should have been the off-season for tornado activity, in a state without the tornado shelter culture of Oklahoma or Kansas. Only the specific meteorology of the next event, its time of occurrence, its geographic location relative to the radar network, its population exposure, and the specific dynamics of its merger geometry will determine which interpretation it falls into. The warning system is performing. The physical constraints on what it can deliver in the worst merger scenarios are real and documented. Strip it back to what the evidence actually says. What is confirmed? Supercell mergers are a real, documented, observationally well-characterized meteorological phenomenon. The specific dynamics, flanking line absorption, outflow boundary convergence, low-level wind shear disruption, mesocyclone rapid amplification are established in the peer-reviewed literature and in the operational meteorological record. The production of rain-wrapped tornadoes from merger events is a known and documented outcome, not a theoretical projection. The WSR-88D network provides genuinely effective tornado warning capability for classic supercell events with visual inflow notches and well-defined hook echoes at typical warning ranges. The 4 to 5 minute scan interval, combined with beam height limitations at moderate to long range, creates a specific vulnerability for rapidly evolving, precipitation embedded tornadoes from merger events. What is confirmed about consequences? Reduced warning lead times are directly associated with elevated tornado fatality rates. The population exposure distribution in the United States is shifting toward the southeastern states, where rain-wrapped high precipitation supercell events and nocturnal severe weather are more prevalent. The thermodynamic environment, CAPE, boundary layer moisture, is loading the atmosphere in ways that raise the potential intensity ceiling for severe convective events. What is uncertain? The specific mechanism of individual tornado genesis in merger events, the relative contributions of outflow boundary convergence versus inflow vorticity, enhancement versus rear flank downdraft dynamics, is an active research area where the NSSL's ongoing field programs, including the Vortex SE research effort focused on the southeastern United States, are gathering data that will improve understanding. Whether specific climate trends are changing the frequency distribution of supercell mergers rather than their intensity when they occur is not yet established from the observational record. What is unknown? Whether the operational transition from the current WSR-88D network to phased array technology will be funded and deployed on a timeline that closes the documented warning time gap before the next catastrophic merger event in a populated area. Whether the wireless emergency alert system's delivery latency under high demand conditions has been characterized and addressed. Whether the shelter availability gap in the southeastern United States housing stock is being addressed at a rate consistent with the observed shift of tornado activity into that region. These are answerable questions. They are not being answered at the pace that the physical risk warrants. The scientific community pursuing answers to the supercell merger and rain-wrapped tornado problem is not working in laboratories alone. It is in the field during active convective events with instrumented vehicles, mobile radars, and balloon-borne instrument packages, trying to gather the near-surface data that the fixed WSR-88D network cannot provide. The verification of the origins of rotation in Tornado's experiment, Vortex, and its successors, Vortex 2 and Vortex SE, have represented the most systematic field research campaigns in the history of tornado science. Vortex 2, conducted from 2009 to 2010 across the central United States, deployed an unprecedented array of mobile observing platforms, mobile Doppler radars, mesonet vehicles, weather balloon units, and instrumented probes designed to be placed in the path of approaching storms, to gather the near-surface data in the tornado environment that is inaccessible to fixed radar networks. The Vortex 2 dataset has produced dozens of peer-reviewed publications on tornado genesis mechanisms, tornado boundary layer structure, and the near-storm environment of both tornado-producing and non-tornado-producing supercells. Research by Paul Markowski at Penn State University using Vortex 2 mobile mesonet data has significantly advanced understanding of the thermodynamic and kinematic differences between supercells that produce significant tornadoes and otherwise similar supercells that do not. Vortex SE specifically focused on the southeastern United States environment, where the expanding population exposure and high precipitation supercell prevalence create a distinct research challenge, has been gathering data since 2016 on the factors that make southeastern tornadoes disproportionately fatal. The program's findings are advancing the scientific understanding of the warning gap problem in precisely the geographic region where the gap is most consequential. Josh Werman at the Center for Severe Weather Research developed and operates the Doppler on Wheels mobile radar platforms, truck-mounted phased array Doppler radar systems that can be positioned in the field to provide high temporal resolution data on storm scale circulation near the surface. The Dow data has produced the most detailed radar observations of tornado structure and evolution available anywhere in the scientific literature. Werman's team documented the El Reno tornado's extraordinary width with Dow measurements that confirmed 4.2 kilometers, a measurement that could not have been made from the fixed WSR 88D network at El Reno's range from the nearest fixed site. The research is advancing. The understanding is deepening. The translation from research understanding to operational capability, the phased array deployment, the warning algorithm improvement, the shelter availability program is proceeding more slowly than the science. At the end of this investigation, the evidence leads somewhere that is both technically specific and broadly human. The supercell merger is not a new phenomenon. It has been occurring across the central and southeastern United States throughout the history of severe weather. What has changed is the population exposure, more people in the path, the thermodynamic environment, more energy available to the storms, and the expectations of a warning system that can handle classic supercell events with meaningful lead times, but encounters its operational limits precisely in the scenarios that produce the most casualties. The primary open loop of this investigation is not cleanly closable because its resolution depends on meteorological events that have not yet occurred and operational decisions that have not yet been made. What the next major supercell merger event will encounter, which city, which housing stock, which time of night, which radar geometry, which atmospheric cape loading, is not knowable in advance. What is knowable is that the risk environment is as loaded as it has been in the observational record, that the warning system's specific vulnerabilities in merger scenarios are documented and only partially addressed, and that the population exposure distribution is shifting toward the geographic and demographic environments where those vulnerabilities have the most severe consequences. The gap between what the science has established and what the operational and policy response has produced is real. It is documented in the NSSL's research publications, in the NWS's after-action analyses of major tornado events, in the academic literature on tornado fatalities, and in the funding history of the Phased Array Radar Program. It is a gap that exists in plain sight, in the published record, mapped in detail by researchers who have spent careers trying to close it. This community watches because paying attention matters, because a supercell merger developing on radar at 2 in the morning in a state with inadequate shelter infrastructure and a warning system working at the limits of its detection capability is a scenario that deserves exactly the kind of measured, evidence-based attention this investigation has tried to provide. Not alarm, not conspiracy. Evidence and the honest acknowledgement of what the evidence cannot yet tell us.
We will be watching the Storm Prediction Center outlooks. We will be here when convective setups develop that warrant examination. We will bring you the radar analysis, the severe weather parameter data, the NSSL research, and the honest uncertainty, every time. Because the question of what two merging storms can produce and what it means for the people living in their path is not a question that resolves between seasons. It asks itself again every spring, and we will be watching.